a current carrying wire or current carrying loop, no, we are introducing this concept of dipole moment. So if you look at the loop, any shaped, any arbitrary shaped loop. So let me first take a circular wire. The current is flowing in it. Let the radius of the wire be E. Then, so there's a current carrying wire. It will produce magnetic field. So I say it will behave like a magnet. There's a ring. Current carrying ring. So shall I say current carrying ring equal to magnet. So we say electromagnet. No, it is electromagnet. So how do you can say you do one thing? Bring some small compass needle. As you start moving it nearby, no, it shows deflection. Then where is the source for magnetism? This current carrying ring itself is behaving like a magnet. So we'll call it as electromagnet. Then rather than saying magnet, better call electromagnet. The moment word magnet comes, what is the first thing we want? Where is the north and south pole? Where is the north and south pole? So let's define first dipole moment. So what is the magnetic dipole moment? The symbol is capital M. It is defined as current into current in a loop by current in a loop into area of loop. So this is equal to current I. What is the area of the loop? Pi a square. And it's a vector quantity. Whatever the direction, curl fingers in the direction of the current. Then the thumb will give the direction of current. Means here what you should do again. Right hand, not left hand here. It should be right hand. So this will be the direction of current and this will give M bar. The thumb will give M bar. So just sense of rotation. So here according to the this is the axis of the ring. So current is flowing in this sense. So how M bar will be here directed along the axis will be vertically up. If the current flows in a ring, what about here? So here I'll change the direction of flow of current. The M bar will be in this direction. Curl fingers in the direction of current. Open up the thumb. Thumb will give the direction of M bar. Now, what is south pole, north pole? The magnetic dipole moment, like you go for electric dipole. In electric dipole, we had like this, minus, plus. How the dipole moment will be directed from negative to positive charge. Similarly, the dipole moment will be directed from south to north pole. We know M bar now. So therefore, this face should be south. This face should be north. I think if you take a ring, no, it will have two surfaces, no? The above surface is south, this will be north. Here, M bar will be directed from south to north. So this is south, this is north. Because all our problems are like a ring. Current carrying loop is what we use application. Where is the application? Where we have come across galvanometer. Of course, we are not using nowadays analog meters. Just go back to till 1990, less than 1990. All measuring instruments were using this current carrying loop. Just imagine, I think it started almost from 1850s. From 1850, it started here. So almost for 140 years, any instrument you take, there must be a current carrying loop. You might have imagined how much of priority they are given for this topic. After 1990, what happened? The digital electronics, solid state electronics came, then things changed. Now we are no longer using any analog meters. But till 1990, almost any quantity you want to measure, there must be a current carrying loop. That's the only alternative available for us. That one. You go to anything, any measuring instrument, so there used to be a current carrying loop. This much of wide application it had. Maybe after 100 years, they should remove this syllabus because no longer will be using analog. Now only we are not using any analog. They have to change syllabus very Almost everything they have to change. If not now, at least after 30 years, they have to change, because what all we learn, all these are irrelevant now. So where do we use, or where is the application? Definitely, I should say only 2% no application. We don't have much now. 98% of application, we stopped using this one. Only 2% still we are using. Okay, don't blame your teacher who is teaching all very old, centuries old topic, because we are learning just fundamentals here, basic fundamentals. Is it okay? No. So south and the north pole. So why we define dipole? If you take the bar magnet, for a bar magnet, south and north pole will be like this. So when you purchase a bar magnet, no, so the first thing the shop person will ask you, what is the dipole moment you want and the shape. So when you purchase a bar magnet in the scientific labs, there if you go and measure in the lab supplies, no, when you say bar magnet I want, it'll ask you what is the shape, magnet, what is the shape and what is the dipole moment. And the dipole moment will be directed from south to north. And how we define dipole moment? We'll define dipole moment as pole strength P into geometric, or so like a magnetic length. There's a magnetic length. Same thing, no? Like what we had dipole moment. Here we'll call that as a pole strength. Small m it is, sorry. Their magnitude of charge into length, dipole moment. Here, so how, what is the charge, no? What is pole strength? Pole strength is called like a magnetic charge. Magnetic charge into separation between magnetic charges. What is the magnetic charge? One south or north pole is called as magnetic charge. So what is our purpose now? To define that, when I say electromagnetism, I should say electromagnet. So where is the south and north pole is needed. So therefore, I'm introducing an idea called as a magnetic dipole moment. How to find out that? Current into effective area. Now, is it for any revolving charge particle, will it have any dipole moment? Because revolving charge particle, will it produce magnetic field? A charge particle is revolving in a circular path. Will it produce any magnetic field?